3. So now by the same logic, if we count the number of total, number of total open loop holes and open loop zeros on the real axis to the right, how many do we have?
0.
0, right? And that's we take it as an even number for this particular discussion. Or in the context of this discussion, we take it to be not odd. Okay. So consequently, what will happen? Like we have this region to be not part of the loop locus. Okay. So I hope it's clear how we got this entire thing, right? How we identified, right, the part of the root locus which lies on the real axis, right? So in summary, for this example, using this step, we have figured out that the region between -4 to 0, okay, lies on the root locus. And why is this important? Because this is important. It tells us how the root locus branch will start, right? So if we once again plot the real axis and the imaginary axis on the S-plane, in this particular example, we have one open loop pole at the origin, one open loop pole at -4. So if you look at the open loop pole at -4, what can so we already know that one branch starts from like one open loop pole, right? So then like we have the open loop pole, this open loop pole at -4 being the nodal point for one of the root locus branches, right? So, but then if let's say we want to start from here, like which direction do we go to, right? And that's where this step helps us, right? Because if we look at we have this branch, we can have this branch starting from -4, starting along infinite directions, right? Is it not? Okay. So consequently, it can go along an infinite set of directions. Then we have the branches going along all the directions starting from -4. But then how do we eliminate and then get the answer, right? So any thoughts on that, based on this step? So if we look at it, see, if I have a branch starting from -4,
sir, angle, sir, angle will be more important thing for that design direction over here. What I mean to say is,
so essentially, Roshan, it's about the direction in which it will start, right? That is the idea, right? Consequently, if we look at which is the direction along which it will start, right? Let's say my question is, can it, for example, can it start along this direction or this direction? Why not? I'm saying it should not, right? I just want us to brainstorm why not, right?
okay, sir.
So I will start with the answers. Maybe as we go along further in the classes, I'm sure all of you will pitch in with your own thoughts. Please note that we are dealing with systems with models having ODEs with constant coefficients and real coefficients, right? So when we have models with real coefficients that result in polynomials with real coefficients, and we solve for the poles, what do you think happens to the what can we say about the complex roots of a polynomial with real coefficients? You remember some discussion which we had previously?
Sir, repeat the question, please. I'm sorry.
So if we have a polynomial with real coefficients, right?
Sir.
What did we learn about complex roots? We learned that if a complex root exists for a polynomial with real coefficients, its conjugate also must be a root, right? Am I correct? Right. So, so in the context of root locus, See, what is root locus? Root locus are the roots of the close to characteristic polynomial, which is a polynomial with real coefficients, right? So now, the root locus branches talks about closed loop poles. So there is only one root locus branch starting from -4, right? And consequently, we can observe that the pole which starts from -4, if it's complex, there should be a mirror image which should also start from -4, right? Is it not? Only then we can have complex conjugate roots, right? We can also have complex conjugate branches, right? So because of this property, right? Polynomials with real coefficients need to have complex conjugate roots. But then how many, the pole at -4 is not repeating. It's only one. It's appearing only once, right? It's a simple pole. So if the open loop pole at -4 is not repeating, we know that there can be only one branch starting from -4. So that eliminates this possibility, right? Of two branches going into the complex plane starting at -4. I hope this argument is clear, right? So now by elimination,
Sir,
yes,
yeah. So can we say if the order of polynomial is equal to the number of roots, then in that case also there is no possibility of having complex conjugates?
no. So can you repeat the question? Order of
Yeah. So
the number of
the
the order of the polynomial, right? Is it not right? Yeah.
yes, sir.
So
There are two roots
obviously,
here, 0 and 4,
yeah,
minus 4.
0. Yes, please.
So if it is 0 and -4 and the order of polynomial is 2, then there are no chances that it should have a complex.
No, in fact, when we plot the root
root.
locus, we are going to have complex conjugate roots, right? So the fact that, see, what is the point here? You know, like, see, you remember that T of s, the denominator polynomial, right? A naught s power 1 plus a1 s power n minus 1 all the way till an minus 1 s plus an, right? In our physical system, whenever we get the transfer function of a system, we are going to deal with polynomials with real coefficients. When we deal with polynomials with real coefficients, we can have complex roots, right? Then the complex conjugate also must be a root. Okay, so in other words, complex roots can only occur as complex conjugate pairs. Okay, so coming back to your question, anyway, we are given an nth order polynomial, it will have n roots. Okay, so you can have real roots, you can have complex roots, or we can have a mix of. All right. So now coming back to this root locus example that we are doing, if we look at the root at -4, the open loop pole at -4, we see that it is appearing only once, right? Its multiplicity is only 1, right? Because there is only one open loop pole at -4. It's not a repeating open loop pole. So consequently, we can have only one branch of the root locus starting from -4. So obviously, it cannot start any direction in the complex plane. Why? Because then by this argument, the mirror image also should be a branch of the root locus, which cannot happen, right? Because only complex roots can occur as only complex conjugates, right? That eliminates all the choices. So consequently, if I can erase all the choices at -4, we will be left with only two choices, right? What do you think are the two choices?
Sir, positive real axis along the positive real axis and along negative real axis.
Exactly, right? So we are left with only two choices. The branch starting from -4 can either go along the direction of the positive real axis, or it can go along the direction of the negative real axis, right? So these are the two choices. Okay. Now the point is which direction it can go along, right? Here we use step 2. So can you tell me, using step 2, which direction it should go along?
Sir, it should be along positive real axis.
Very good, very good. Why is that?
Because it should lie between -4 to 0.
Excellent. Like, so please note that the region between -infinity to -4 is not part of the root locus. The region between 0 to 4 is part of the root locus. So the branch starting at -4 should only go along the positive real axis, because If it goes the other way, we have already figured out that that part of the real axis is not part of the root locus in this problem, right? So I hope it's clear why it starts to the right. Now, using the same argument, how do you think the branch at 0 will start?
Other direction, sir, because on the right side of that, there is no like plane in that sense.
Very good. So because 0 to infinity is not there on the root locus, obviously there is no repeating open loop pole at the origin. So there can be only one branch starting from the origin. Obviously, it cannot go along the along any complex plane. Why? Because the complex conjugate branch also must be a branch of the root locus. So using all these arguments, right, whatever you and I have already used, right, the root locus branch at the origin can only go to the left, okay, from the origin, okay.
Sir, one request, sir.
Yes, please.
The statement that you have given about like root at the -4 can have the different possibility of going in different directions, and we have concluded that it will move towards I think right side because of it's a real play, the roots level, and the argument that you have given. I think that is partially like we have understood it, but I'm thinking it's little busy in that sense. Please. So can you just
let me repeat it once more. Let me repeat it once more. Right.
Thank
I
you,
will
sir.
not clutter the -4 point. I will take only one branch. Right.
Right.
So
Okay.
let's say we look at -4. Right. As we already know from step 1, every branch of the root locus must start from an open loop pole. Right. Yeah. Okay. So then the point is, what do we do, right? So as far as the the open loop pole is concerned, right? So then the question becomes, it can go in infinite directions, right? So first, let's look at what happens if it goes along the any direction in the imaginary axis, right? Let's say the branch starts arbitrarily in this direction. So by the argument that we made about complex poles of the complex conjugate poles, or complex poles only appearing as conjugate pairs, this branch also must be a root locus, right? But then we essentially know that there is only one branch which starts from one open loop pole, right? So this cannot happen, right? Because there is only one open loop pole at -4. So we cannot have two branches starting from -4. So this rules out this possibility. Which possibility? That is the pole at -4 starting along any complex direction. All right. So that is what is ruled out. Now, by ruling it out, we go along the only two possibilities which are left are the two real axes, right? The positive real axis and the negative real axis. We just argued, right? I hope that part was clear, Roshan, right? So why the direction towards the negative real axis, is not possible, right? Yeah.
Right, sir. That is clear, sir.
So
only one. I
yes,
will ask in a different way, sir. Will there be a possibility will exist that like -4, which we are telling that there is only one pole over there, so hence the conjugate roots cannot appear, right, sir? So will there be any possibility where that conjugate planes exists?
Absolutely. Even in this example, we are going to look at that. But then, to answer your specific question, let's say we have a system where, let's say there are two open loop poles at -3. Okay, there is a repeating open loop pole at -3, right? Then you can have complex conjugate branches.
The equation will be s plus 3 whole square, right? So in that sense,
exactly, right? In the denominator of the open loop transfer function, you will have s plus 3 whole square, which will result in a repeating open loop pole at -3, which in turn will lead to a pair of complex conjugate branches, right? So the argument that you and I made for the example that we are considering is because the pole at -4 occurs only once. That's what is called as a simple pole, right? Simple poles are non-repeating poles, right? That is the reason why, we essentially are unable to, go along the complex direction, right? In this particular example, I hope that
Clear,
clarifies.
sir. Clear, sir. Clear, sir. Absolutely clear now. Right, sir. Thank you.
Fine. Okay. Welcome. Any other questions before we move to the next step? All right. Okay. So now we understand the importance of step 2, right? Let's go to step 3. So once again, I'm going to give intuitive explanations of these steps, right? And then we will see where we go, right? So in step 3, you and I will determine the asymptotes of the root locus. Okay. Please remember, for causal systems, m should be less than or equal to n, right? If m is equal to n, we don't have this step, okay? Because the root locus will have n branches. Each branch will start from an open loop pole, and each branch will end at an open loop zero. So there is no problem when m is equal to n. Or I should not say no problem. The asymptotes don't exist when m is equal to n. So asymptotes will exist only when m is less than n. Okay. So let's read through this condition. So determining the asymptotes of the root locus, this step will apply only when m is less than n. If the test point is chosen very far away from the origin, then the angle contribution of each open loop pole cancels with that of an open loop zero. We will figure out why. Then the asymptotes will be straight lines which will make an angle with a positive real axis of plus or minus 180 degrees times 2k plus 1 divided by n minus n. And then the point of intersection of the asymptotes on the real axis is given by the formula sum of open loop poles minus sum of open loop zeros divided by n minus n. Okay, so this is the step for calculating the asymptotes. Now, why is this the case? Okay, let's go and understand. So let's take this example. Okay, so I'm considering this schematic where we have a pole, open loop pole at minus p1. And then open loop 0 at minus z. Let's consider, the general case, right? So where we have the open loop transfer function as k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pm. Okay. Now, if we look at this particular open loop transfer function, right? So we have if we apply the angle condition, it will be the angle of the algebraic sum of each factor, right? Or algebraic sum of the angle contribution from each factor. So it will be angle of k, angle of s plus z1, all the way till angle of s plus zm, minus angle of s plus pn. Why did we get the minus sign? Because s plus p1 is in the denominator. So we need to subtract the angle of s plus p1, and then all the way till s plus pn. Okay. Now, let us say for the purpose of understanding, we consider minus P1 and minus Z. Okay, without loss of generality, right? And then I take a test point ST here. Okay, so if you and I want to get the angle of ST plus Z1, it is the angle of ST minus Z1. So in other words, it is the angle made by the vector drawn from minus Z1 to ST, okay, which is we have represented as theta 1. Okay, here. Similarly, if you and I want the angle ST plus P1, it is the angle made by ST with the vector drawn from minus P1 to ST, which is this vector. Okay, and that angle we have labeled as phi 1. Okay, I hope it's clear how we got these angles. Right now, let us say we move ST far away from the origin and far away from the poles. What do you think will happen to these
It will
angles?
become parallel to real axis.
Angle will be near to zero.
Not to zero. Yeah.
Yeah. I think thanks for the response. So let me just give you some more hints so that we arrive at the correct answer. Right? Let's say we move this ST far away from the origin, anywhere in the complex plane, right? What can you say about the numerical measure of theta 1 and phi 1?
Sir, it could be either 0 or 90 degrees.
So, in fact, of course, we are looking at only ST from either along the real axis or the imaginary axis. But I will give you the answer. Then you tell me why. If
So
I
it will
move,
be equal, sir. Theta 1 will equal to phi, actually, in my opinion. Like if we move the ST far away
Yeah.
from the origin,
exactly.
both angles will become equal. Whatever
So,
value it will be.
yeah, if
of
I
the
move ST far away from the origin, you can see that asymptotically, the angle theta 1 and phi 1 will become equal to each other. Okay. So that is the important observation. You can think about it, right? So let's say I have ST here. Okay, for the sake of argument, I draw the vector ST plus P1. Oh, sorry. It's a very bad line which I have drawn. Doesn't even look like it. Oops. Let me draw the line vector from this. Okay, then we draw this, right? You can immediately see that these angles slowly are becoming closer and closer, right? So this will be theta in this case, this will be phi in this case, right? So you can see that as ST keeps going away and away, the angle made by these vectors are going to sort of like converge to the same value, right? So now we get the hint, right? So angle of K is 0 because K is positive. Angle of S plus Z1 through S plus Zm will all be theta. Okay. So I will have theta coming M times minus theta repeating NP an odd multiple of pi. Why? Because there is the angle condition for root locus, right? So you and I are checking which point at infinity will lie on the root locus, right? That's the objective of this asymptote, okay? Of figuring out asymptote. Asymptotes are the directions along which the root locus will ultimately tend to when m is less than n, right? So this will be m times theta minus n times theta. This will be plus or minus 180 degrees times 2k plus 1. So what do you think will happen? Theta, which is the angle made by the asymptote, will now be 180 plus or minus 180 degrees times 2k plus 1 divided by n minus n. Okay, k going from 0, 1, 2, etc. Okay, so I hope it's clear how we got this formula, right? Okay. So any questions? You want me to repeat anything here?
Yes, sir. Once, please. I'm sorry.
So,
Please,
so once again, we look at this open loop transfer function g of s h of s, which is k times s plus z1 all the way till s plus zm divided by s plus v1 all the way till s plus vn. So if we look at the angle condition, we get it like this. Then, the angle condition is the angle made by each of these factors should be an odd multiple of 180 degrees. So as we take a test point which moves farther and farther away from the origin, we argued that the angle contribution from each open loop 0 and each open loop pole is going to converge to the same value. So when we write this angle condition for a test point chosen at infinity, we will have the angle of each term being theta. So in the for the zeros, we will have m times theta. For the poles, we will have n times theta. Okay, but then we need to subtract them, right? Because zeros, the factor involving the zeros are in the numerator. The factor involving the poles are in the denominator, right? So that's why we end up subtracting them. And then the angle condition, or the angle, right, made by this what to say, asymptote, right? The formula comes out to be plus or minus 180 degrees times 2k plus 1 divided by n minus. Okay, so that's how we get to this particular expression. I hope it's right, sir.
Yeah, sir, am I audible?
Yes, please.
Prem here. Just one doubt. Maybe this is silly, but why do we subtract those two angles when it is in denominator?
So this is from complex algebra, Prem. Okay. So let us say you have, sorry, in complex algebra, let's say we have some function p of s, right? Which is n of s divided by d of s, right? You want to find the phase of this p of s. It is the phase of n of s minus phase of d of s. Okay. This is a result from complex variables. Okay. Right. Hello.
Clear, sir. Clear, sir.
So to give an example, let's say we have 1 by s plus 1, right? So if you want to calculate the phase of this, this is the same as minus of phase of s plus 1. Okay, so that's it. All right. So that's
Yeah,
how.
understood. Understood. Yeah.
All right.
And
So
sir, how do we represent this theta asymptote on the graph?
no, it is just a dummy variable.
This is a value. Value. Okay, sir.
Right.
Okay,
So
got it.
we
Okay.
calculate the value. See, first I wanted to motivate how we got the formula. Now we will go back to the example. Okay.
Okay,
Okay.
sure.
So now we
Sure,
go
sir.
back to our example. In our problem, the value of n is 2 and the value of m is 0. Okay. So what will be the angle of the asymptote? It will be plus or minus 180 degrees times 2k plus 1 divided by n minus m. N minus m happens to be 2. So we get plus or minus 90 degrees. Okay. So which we can write as 90 and 270. Okay. So these are the angles made by the two asymptotes. Okay. So because there are going to be n minus m asymptotes, n minus m in this case is 2 in our example. So that's why we are having two asymptotes. Now we go and answer the question which Prem asked yesterday, right? He was asking what is this 90 degree, 270 degree and so on, right? That's the asymptote which I have drawn. So the blue dashed line which I have drawn here indicates the two asymptotes. So now it's clear. I hope it's clear why I drew 90 and 270 degrees. Okay, yeah. All right. So we asked this, we discussed this question. I told that I will discuss it tomorrow, right? I hope this is clarified. Okay.
Clear, sir.
But then we still need to find out why did I draw the two dashed line intersecting at -2. That is because of the point of intersection of the asymptotes, right? You remember the formula for point of intersection of the asymptotes? This I leave it to you as an exercise to figure out. Okay. So because I don't want to convert this into a course on fundamental math, right? And also to keep things interesting, I think I should also give you exercises to figure out, right? So one can show that the point of intersection of the asymptotes just becomes the sum of open loop holes minus sum of open loop zeros divided by n minus. So I derived the formula for the angle. I request you to derive the angle formula for point of intersection. Okay. So we are just going to use that. So if I use, if I use that, what will happen? Sum of open loop holes means what are the two open loop holes? 0 and
0 and -4.
0 and -4. So this is the sum of open loop holes minus sum of open loop zeros. There are no open loop zeros in this example. Divided by n minus m is 2. So what do we get? We get -2. Okay. So I hope it's now clear why I drew this asymptote 1 at an angle of plus 90 degrees and asymptote 2 at an angle of minus 90 degrees or 270 degrees, right? I hope this is clarified. I hope, Prem, now this complete diagram is clarified, right? Along with the multiple arrows which I have drawn here, right?
Yes, sir. Yes, sir. Very clear.
Okay. All right. Okay. So this is step 3. Okay. So determining the asymptotes for, like the root locus. All right. So any questions on step 3? Okay. So I will briefly introduce step 4. We will continue in the next class. Okay. So what is step 4? Step 4 is to determine what are called as the breakaway and the break-in points, right? Let me motivate what is the breakaway and break-in point, and then we will start from here the next class. So if you look at this graph, see, we concluded that one start from -4 to the right. Another branch of the root locus will start from 0 to the left. So as k keeps on varying, these branches will keep coming towards each other, right? At some point, they are going to hit each other, right? Correct? They are going to intersect at some point of K. Then what will happen? What will happen is that at that point, they will move away into the complex plane, because now you have two branches which essentially hit each other, and then they go to the complex plane. Okay. So such a point is what is called as a breakaway point. I hope now the English term is clear. What is a breakaway point? The breakaway point is a point at which two branches of the root locus, which were on the real axis, right, go into the complex plane. Okay, that it is breaking away from the real axis. Okay, I hope the meaning is clear. Similarly, let's say in this example, it's not there. Let's say there are two real open loop poles on the real axis. Let's say we figure out that the two branches end like this. What happens is that we will have what is called as a break-in point. Okay, so there will be branches from the imaginary axis which will come in, and then which will get into this break-in. Okay, so essentially we have this particular what to say characteristics. Okay, so I hope the definition of breakaway and break-in point is clear, right? Okay. Any questions on the definition of the breakaway and break-in point? We'll figure out how to determine the breakaway and break-in point in the next class on Monday. Okay, but any questions on the definition of breakaway and break-in point? So what, like in the next class. So let's forget the what to say terms in the parenthesis. So right now I will only read the terms outside the parenthesis in step 4. So a breakaway point, for example, will exist on the root locus between two consecutive open loop poles on the real axis with no real open loop zeros in between them. That's what happened in our example, right? We had two consecutive real open loop poles, one at 0 and one at -4, and that's what we have. All right. So if the characteristic equation is written as 1 plus k times a of s by b of s, a of s is going to be s plus z1 all the way till s plus zn. B of s is going to be s plus p1 all the way till s plus pn. Then the solution of the equation b prime s as minus b of s a prime s, where prime indicates one derivative with respect to s, equal to 0, will provide possible values of s where breakaway points will exist. Why is this the case? How do we deal with it? Like from an engineering perspective, we will look at it in the next class. So once again, I want to provide a very intuitive notion of breakaway and break-in points, in fact, of all the steps, right? So that like you and I understand what's happening, and then like we construct the root locus, right? Of course, one may get the question, hey, why are we studying all this math in a course on automotive controls, right? Because we will see that when we design at least first level controllers for automotive applications, the idea of root locus is quite useful. Okay, so for us to use that idea, you and I need to know a little bit of this theory, right? So only then you and I can interpret it when we are trying to design it for our automotive application. I hope that thought process is clear, right? Okay, fine. Okay, so we will stop here. Okay, and we will continue from here in the in Monday's class. Okay, we look at the remaining steps and then we will go from. All right. Any questions?
Too many concepts. We have to assimilate all this.
Yes.
Very intricate and fine concepts, I would say, sir.
Yes, Roshan. Yeah, but once you understand, it is like learning any other subject or art, right? Till we learn it, the process may be a little bit challenging. But once you learn it, things become pretty straightforward. Okay, so that's what I would say, right? So and of course, as I told, the reason why I'm teaching all this, I would say math completely, but the perspective of the math, right, is because I have found that having this perspective is quite useful when we want to do real life design, particularly in the automotive. Okay, so that is my motivation. I hope that's clear. Okay.
Thank you, sir.
Okay. Any questions before we close today's class? Arnachalam, is everyone present in today's class? No.
Yes, sir. Yes.
Yes, sir. Yes, sir.
Okay. So I mark attendance for everybody. Okay. So then we will meet next Monday at 5. All right. And then we'll continue from here. Okay. Thank you.
Thank you, sir.
Thank you,
so
sir.
much, sir. Thank you so much, sir.
Yeah, please
you,
go
sir.
through this document over the weekend. Okay. So that you will also, maybe gain your own perspective and then like come up with some questions on Monday. Okay.
Sir, one question I want to ask, just like any book, I was referring to Ogata, but it was I think so I could not get many things.
In fact, I have simplified things and then presented it, Roshan. Like if you open Ogata or any other controls textbook, you will see a lot of mathematics,
Okay,
right? So that's why I teach in my own way, so that I sort of share some engineering insight. Let me put it that way. Okay. Yeah.
Thank you, sir. Thank you.
So once again, you can watch the videos on NPTEL, right? So I would have gone a little bit more in depth. Okay, so that you can pick
Sure,
up.
sir.
Right? So,
Sure, sir. Sure.
okay.
Thank you,
Okay. Okay. Thank you all. Have a good weekend, and then we'll meet once again on Monday. Right? See you.
sure, sir. Thank you, sir.
Thank you, sir.